our world and beyond. Space, in partnership with the European Space Agency.
Scientists have traced a unique new map of the first light of the universe and raised profound questions about the Big Bang.
It is the universe. It's the universe that we live in, and we are interested in it, I think. That is a basic question we all ask ourselves. Where did we come from? How do we fit into this big picture?
The idea that you can actually experimentally test what happened at the Big Bang, it still amazes me.
So the idea behind Planck was to do the ultimate experiment in mapping the heat left over from the Big Bang.
And that ultimate mapping experiment contains information no one in science was expecting to see.
So we're going to see a very special image. It's the image that we have made with the Planck satellite of the cosmic microwave background. And it displays in its full glory a lot of work that we've done over the past few years. So let's go.
The cosmic microwave background is light or heat that was emitted just 380,000 years after the Big Bang. At that time, light was closely linked to matter, so mapping it tells us a lot about the structure of the early universe.
An orange spot or a blue spot, they are spots which will, in fact, evolve. They are spots which have slightly higher or slightly lower densities of matter at that time, and will continue to evolve and become more and more dense, or less and less dense, and in fact will turn into the kind of structures that we see today. So they will turn into stars, and then these stars will aggregate into galaxies, and the galaxies will aggregate into clusters of galaxies. It turns out that most of this image, most of this map, fits beautifully our very simple model. At the same time, we find some strange things. And this is where it starts to get interesting, because we see some signs of things that do not fit. Roughly speaking, the things that we are finding that are not as we expect are features that are across the whole sky. Right? And they're not easy to see by eye. But if I point at some of them, you may see them. For example, we find that over here there is a so-called cold spot, which is a large area of the sky where we find some deficit of signal. Right? We would expect to see more signal there, and we don't. So that's clear anomaly, if you like. But this is an easy one to point to because it's fairly well localized. When we look only at the large features on this map, you find that our best fitting model, our best theory, has a problem fitting the data. There is, a lack of signal that we would expect to see.
Planck is a European Space Agency mission with a huge scientific following, including here in the US. Professor Bruce Partridge was amongst the early contributors to the project. He knew that to unravel the Big Bang and its aftermath, the mission had to deliver unprecedented resolution.
Planck is the first survey of the entire sky at a range of wavelengths that are difficult to see from the surface of the Earth. From a frequency of about 100 gigahertz, which corresponds to wavelengths of a few millimeters, up in frequency by nearly a factor of 10. Planck is the first instrument to survey the entire sky with any sensitivity at all. Think for a moment about the advances in cameras as they went from a few megapixels to 6, 8, 12 megapixels. Basically, Planck is making that same leap upwards, much higher resolution and higher sensitivity in mapping this surface.
Even with high resolution, the scientists had to be sure they weren't picking up misleading interference from objects much closer to Earth.
We live in a galaxy which itself is emitting heat radiation, and that can spoil or mimic this heat left over from the Big Bang, so you need to control for that. So Planck was designed with a number of different frequency bands sensitive to the emission from the galaxy or from background radio sources, so we could get rid of those effects and get at the cosmic signal from the hot Big Bang.
The result of such precision is that Planck has given us our best ever view of the cosmic microwave background. It's a view that's left the great minds here in Cambridge, England, spinning with ideas.
What we think happened was that the universe went through a phase where it accelerated faster than the speed of light. And so a tiny little patch could expand incredibly fast and make the universe, the entire universe that we see today. So you start off with a small patch and it inflates and becomes very, very large.
That concept is known as inflation, and it's being challenged by the observations that have been made by Planck.
We see these strange patterns that are not expected, in inflationary theory, the simplest inflationary theories. And so there's a real possibility that we have an incomplete picture. It may be that we've been fooled, that inflation didn't happen, and it's perfectly possible that there was some phase of the universe before the Big Bang actually happened, where you can track the history of the universe to a pre-Big Bang period.
So the Planck mission could test ideas about how the early universe was formed. The puzzle is that at small scales the data fits the theoretical model very nicely, but at larger scales the signal from the cosmic microwave background is much weaker than expected.
Can we find a theoretical explanation that links together the different phenomena that we've seen, the different little discrepancies with inflationary theory? And that's where there's the potential for a paradigm shift, because at the moment there's no obvious theoretical explanation that links together these anomalies that we've seen. But if you found a theory that links phenomena that were previously unrelated, then that's a pointer to new physics.
It appears that this audacious mission really will shed new light on what happened at the dawn of time. Planck's precision instruments offering a rich mine of real data for cosmology.
How old is the universe? Is it really expanding? Did it start in a hot Big Bang? And the answer to those things are coming out of these observations. Yes, it did start not Big Bang. We know how old it is. It's 13.7 billion years. Not 14, not 15, but 13.7 billion years old. These are questions that we're answering observationally. And questions, in a sense, that have been with humanity for many millennia, in my lifetime, are getting answered. Sharp, precise, physical, observationally based answers.
This map is not challenging the basic observations that we have already made. For example, the expansion of the universe has been measured, it is there. It's not going to change. What it is changing is our view of how the universe began, of what are the phenomena that happened at the very beginning of the universe, what people call the Big Bang.
At the same time as having beautiful experimental results that fit with simple models of what might have happened at the Big Bang, but that don't quite fit, is perhaps not a surprise. That we haven't got the physics, the understanding completely right yet. And that means that there's plenty of work to do in the future.